Okay, so this is the outline of chapter 22 about the electric field. So the outline here is the first one is to define what is an E field, the electric field, and then we will start to compute the E field generated by different charge structure. Okay, like the first one is electric field due to a single charge particle, and then the electric field due to a dipole. A dipole is actually a pair of charge, and then the electric field due to a line of charge, and then starting from here we start to introduce some calculus here. Okay, and then we will also try to compute the electric field due to a charge disk, and then finally 2 point point charge in an electric field, and then a dipole in an electric field. So this is a little bit different, but the second to the fifth part is to evaluate the E field, and then the last 2 points is to actually put a charge or put a dipole in the E field. Okay, so this is the E field. Okay, so here is in this figure we can see on the left side there is a charge called Q1, and then on the right side there is another charge called Q2. Okay, so in this charge both of them are positive, but it doesn't really matter whether they are positive or negative. Maybe it also works if one is positive and one is negative. Okay, so here the question is, what does particle how does particle 1 know the presence of particle 2? Okay, 他问为什么 Q1 知道 Q2 的存在？为什么问一个这么哲学的问题啊 ？Okay, so because in the previous chapter, what we learned is if we have two charged particles, then there will be Coulomb's force, as you learned in the previous chapter. F equals K times Q1 Q2 over R squared. Okay, so this is the Coulomb's force. Coulomb's force. Okay, and actually the point here is the particle does not touch each other. But there will be a force acting on it. Okay, so in this figure, they are all positive charge, so there will be a repelling force. There will be repelling forces acting on each of them. Okay, how does Q1 know the existence of Q2? If we put a paper in between them, okay, the forces are still there. So how does Q1 know the existence of Q2? So that there will be a force acting on Q1 and vice versa. Okay, so this is a philosophical problem. Okay, so actually here he also asked that how can particle 2 push on particle 1? Okay, so similar meaning. Okay, so particle 1 know the existence of particle 2, and then how can particle 2 push on particle 1? Okay, how can there be such an action at a distance? Okay, so actually this is similar to the gravitational force. For the gravitational force, the idea are similar. Okay, so the gravitational force, it is actually F equals G times M1 M2 over R squared. Okay, actually the situations are similar. The only difference is that they consider M1 M2 are the masses of two objects. Okay, and there will be forces attracting them. Okay, so this is the gravitational force. Okay, so both of them okay, so the two objects doesn't touch each other, but there will be force acting on them. OK， 所以中文的话，这个叫做超距离超距离就是没有接触，但是不是这个距，超距。没有接触，但是有一段距离，但是又有个力我可以隔空作用在某个东西上面那现实当中如果我能够这样去推动那个瓶子的话，那就是魔术或者是特异功能，或者是骗人的。OK， 但是实际上这个电磁力跟重力的话，就是一个超距离。 Okay, so here the explanation that we shall examine here is this. So it says the particle 2 sets up an electric field, or in short form E field, at all points in the surrounding space. Okay, even if the space is vacuum. Okay， 所以它的意思是说，particle 2如果它是一个电荷的话，它就会产生一个电场，它会产生一个电场啊，就算在真空当中也会有啊，就算在真空当中也会有。Okay, so actually for the charge, as long as it is a charge, okay, it will generate a field, something like this, E field, all over the surrounding space, okay. 就是在空间上面每一个点都会产生一个场啊，这个叫做电场 E field. Okay, so if we place particle 1 at any point in that space, particle 1 knows the presence of particle 2 because it is affected by the electric field particle 2 has already set up at that point. Okay, 所以它的意思是 Q1 不是感觉到 Q2 的存在 ，Q1 是感觉到 Q2 所产生的场。在这一点啊，只感觉到在这一点 Q2 所产生的电场 ，OK。Also, thus particle 2 pushes on particle 1 not by touching it as you would push on a coffee mug by making contact 啊，所以它就引入一个场的概念啊，引入一个场的概念啊，我是一个电荷，我就会产生场啊，在空间上面不同的点，它场的大小方向都不一样啊，但是你只要在这个空间的某一个点，它就会感觉到那个点的场当然有电场可能也有磁场或者是重力场各种的场。Okay, instead particle 2 pushes by means of the electric field it has set up 所以换个角度的话，就是Q2 是透过它产生的场去推动这个 Q1 这个电荷。Okay, so here this page starts to define what is an E field in a mathematical way. So it says the electric field E at any point is defined in terms of the electrostatic force. Okay, so this is the definition. Is the electrostatic force, or we can call it Coulomb's force, as we call it in chapter 21. Okay, that would be exerted on a positive test charge Q0 placed there. Okay, so positive test charge is just a test charge, so it's just used for the definition. In the real world, this Q0 doesn't necessary to be there, or doesn't necessary to be exist. Okay, so actually the definition is something like this. E is the E field. E is the E field. And then it is defined to be the electrostatic force divided by this Q0, okay? Because if you need to define this force, there must be another charged particle. So we assume there is a positive test charge, and then and what is important is this should be positive. This should be positive. If it is negative, the direction of the force is the other way around. So we need to let the test charge to be positive, and then if we put a charge at this point, okay, and then there will be a force acting on it as much as this. Okay, we would like to know the E field generated by this stuff. So it will generate E field all over the space, and then of course if we also put this charge here, this test charge will also generate E field, but here what we concern is the E field generated by the top big negative charge. Okay, so here what we try to put this test charge here is there will be a force acting on this test charge, and the force is pointing upwards. So we have this F here, and then we can define it by Q0, define it by Q0. So this is the definition of E field. So we can see that as much as Q0 is positive, so the E field also points to the same direction, but only with a normalization factor Q0. If we try to put the pass charge Q0 here, and there will be a force acting on it pointing to the right side. And in that case, that point will have an E field also point to the right side. Okay. And yeah, as I mentioned, what is important is the SI unit of a physical variable. So the SI unit for the E field is N over C. N over C. Very straightforward because the SI unit for the force should be Newton. Okay, N, and then the SI unit for the charge should be Coulomb, what you learned in chapter 21. So N over C is the SI unit of E. And actually in chapter 24, you will also learn another SI unit for the E field, which will be V over M. Okay, both are correct. If you try to answer in a quiz or exam, okay, N over C and V over M are all correct for the SI unit of the E field. Okay, so this is a definition. Of course, it is too simple. We need to use it in another way. Because in chapter 21, we also know that this electrostatic force or the Coulomb's force is actually F equals 1 over 4 pi epsilon naught, and then times maybe we call it Q. Okay, so this will be Q times Q0 over R squared. This will be R, so R squared. So if we put this Coulomb's force into here, we will see that E will be 1 over 4 pi epsilon naught, and then times Q, and then Q0, and this Q0 cancel each other, so it remains capital Q over R squared, and then times 1 over 4 pi epsilon naught. Okay, so this will be another important equation you use later on. Okay, so far it is still very simple. You should have learned it in high school physics. So here we also introduce another concept called the E field lines， 就是叫做电场线 electric field line or E field lines. Okay, so the E field lines help us to visualize the direction and the magnitude of the E fields. Okay, 所以就是 visualize 就是视觉化。Okay, so so this E field lines should satisfy these two rules. So the first one is the electric field vector at any point is tangent to the field lines through that point. Okay, 所以这的话，它是说，每一点都有一个电场嘛。那我们可以把那些电场就顺着顺的连起来，顺的连起来。那怎么顺呢？就是说，那个线的话，就是每一点的话，它的切线方向就是那个点的电场方向那个点的电场方向。Okay, so the E field vector at any point is tangent to the field line, tangent to the field line through that point. Okay, 因为那些电场线可能是曲线那你要知道当你画出那个电场线之后我要知道某一点电场的方向的话，你就画个切线，然后它就会有一个方向的从哪边到哪边，那顺着那个方向就是那个电场的方向。And then the second rule, okay, so the first rule is about the direction. It's about the direction. Okay, so the first point is about the direction. And the second point is about the magnitude. Although it is not an absolute value of the magnitude, it's only a comparison. It's only a comparison. So the second point is that the density of the field line in that region is proportional to the magnitude. Proportional to the magnitude. Okay, so proportional means 正比嘛，正比的话就是只是一个比例的关系，它没有告诉你说这个电场到底多大，只是说相对来说 A 跟 B 点哪一个比较强而已。Okay, so it's proportional to the magnitude of the electric field there. Okay, so for the first example is this one. We have a negative charge, so all the E field line are pointing towards this negative charge. Okay. in a radial direction 啊，radial direction 就是那个径向，radial direction 啊，那个径向就是那个是球坐标径向 radial direction。Okay, and then so this is so this is the easiest case. And then for the second one, we have a plate. We have a plate with uniform charge density. Okay, so in that case, it will generate a uniform E field pointing to the right side. Uniform E field pointing to the right side. So you can see here, okay, so it will generate uniform E field to the right side on the right side of the plate, and then it will also generate uniform E field pointing to the left side on the left of the plate. OK， 左边就会产生向左的均匀电场，在右手边就会产生向右的均匀电场。这个就是一个无限大的板子有一个均匀电场会产生这样的一个电场的一个 structure 在后面的话会告诉你说为什么这样后面会推导。那现在的话就是告诉你说这个是如果是均匀的话，就是你随便画一个圆圈等面积的它就框住两条线它的密度就是一样的，就是大概是那个感觉，就是你所有的平行线嘛，所以那个密度就是一样的嘛，所以就是哪一点的电场都是一样的，它就是这么表达。那这个的话就是比如说我在接近这个就是左边这个图如果我用一个圈在一个接近那个电荷的位置这里圈一个它可能就圈出3-4根线。那如果在很靠近外面的画一个差不多大小的圆圈它只框住一条线或者2条线，那就表示说靠近那个电荷是比较强的电场靠比较远的就比较弱。So this is the rule for the electric field line. So one is for the direction, Okay, in this case, both of them are straight lines. So the tangent line is actually follow the straight line. If it is a curvature line, so then you need to find the tangent line， 就是找那个切线。那第二个 rule 的话就是跟 density 的话就是线的密度就会正比于这个电场的大小，就是刚才我说的。Okay, so in this page, it's also said that electric field lines extend away from positive charge where they originate and towards negative charge where they terminate. 就是说这个是另外一个规则，是说这个电场线一定是从正电荷开始，然后从负电荷结束从负电荷结束。所以你看到这个的话，就是从负电荷结束，但是没有正电荷，那正电荷就是在无穷远处，所以就是无穷远处过来到这边结束。那这个的话就只有正电荷在中间，所以所有线都从这个板子都从这个板子开始然后因为这个也无穷大，所以你可以想象它是一个无穷大的，那负电荷在无穷远的左边跟右边，所以它就全部都指左边就指左边，右边指右边。Okay, and in this case we have two positive charge here. Okay, we have two positive charge here, so the electric field line will look like this. Okay, so actually it also satisfies this rule, okay, which means that both of them are positive charge, so all the E field line are positive, and then there are no negative charge, so which means negative charge are infinitely far away. Okay, so all the lines are going to infinitely far away. And actually, it also said that the electric field vector at any given point must be tangent to the field line at any point and in the same direction, as shown for one vector. A closer spacing mean a larger field magnitude. Okay, 所以也是说，就是比如说在这边就比较强嘛，就远的就比较弱嘛。然后其实中间也很弱， 中间的话其实是怎么说，就是他们两个会互相抵消，所以在中间的点是 perfectly zero 的，在终点的位置。那靠近终点的位置也会有很大程度的抵消，所以就会很弱。所以看到那些电场线是中间就抛开的，那中间就没有啊，中间就没有。And then it also asks a question: does the pattern itself suggest that the particle repel each other? Okay, so this is not that rigorous， 就是不是很严谨，但是大概是这个意思的话，就是说这个电场最多的话是指上下的方向，指上下的方向啊，上面是没有的。所以的话，就代表说这个正电荷就会跟着这个电场方向去跑，这个也是，所以它应该会往下跑。左右的话会抵消掉啊，左右的话会抵消掉，所以它就会往上跑，往下跑，就会排斥。Okay, so here this is electric field due to a charged particle, which is what I derived in several few pages before. Okay, so it says the magnitude of the E field set up by a particle with a charge Q at distance r from the particle is this one. Okay, so this is nothing but E equals F over Q. Okay, and then the Q and the Q in the Coulomb's force cancel each other. So here we only have a single Q in the numerator, and then the other stuff are exactly the same. Okay, so here this is the vector form. So we also have an R hat here. So for this case, we only have a single charge. So in that case, the R axis for different point in the space is defined by, let's say, we consider this point. Okay, so the R direction is actually starting from this charge Q, and then you try to connect this charge with the point you concern. Okay, so the direction of the R is something like this. Considering this point, and then the R head is somehow pointing to that direction. So in such a way, if Q is positive, so other terms are also positive. So in that case, E points to the same direction as R hat. If Q is negative, and then E and R hat points to the opposite direction. Okay, so in this case, Q is positive. So in that way, E vector also pointing to the same direction. Okay, so below, so here it says the electric field vector set up by a positively charged particle all points direct away from the particle. Okay, 所以正的话就是方向就会离它而去。那 those set up a negative charge particle all point direct towards the particle. 负的话就是全部都指向它。Okay. If more than one charged particle set up an electric field at a point, the net E field is the vector sum of the individual E field. E field obeys the superposition principle, 叠加原理。So it is similar to the Coulomb's force. If there are more than two charged particles, then you need to calculate the Coulomb's force one by one, and then you use the vector sum to add them together. So as this case, if there are more than one charged particle, so all of them will generate E field in the same space. So for each point, you need to calculate the E field generated by each charged particle, and then you use the vector sum to add them together. Okay, so this one we cannot use it anymore. This is a JavaScript, so it is already out of date. We cannot open it anymore. Okay, so here it's a sample problem 1. Okay, in this chapter. So here it says figure A here shows 3 particles with charges Q1, Q2, and Q3. Okay, so this is Q1, this is Q2, this is Q3, this is Q. So we only have the Q1, Q2, Q3 here. Okay, so each with a distance d from the origin. What net field is produced at the origin? So it asks you the E field generate at the origin， 就是原点的电场。因为如果整个空间的电场的话，就是要一直算的，所以通常你要用一个 computer software 才能够算出整个空间的。那通常题目的只会问你一个点，除非它很特殊的话，才可以算出来不止一个点。但后面的话，可能有一些公式告诉你说，比如说一个轴上面会怎么样，或者一个平面上面会怎么样。但是这个一开始的话，就是问你一个点是怎么样。So so actually Q1 is plus 2Q, and then Q2 is negative 2Q, and then Q3 is negative 4Q. Okay, so we start to compute E1 hat. E1 vector is actually K times 2Q over d squared. Okay, all the distance of the charge particle to the origin are all d. Okay, so we use d squared in the denominator. Okay, and we have R1 hat. Okay, how do we define R1 hat? R1 hat is actually like we have this charge here, and then the point we concern is here. So the R-axis correspond to Q1 should be something like this. This is the R1 axis. Okay, so in that case, R1 hat is pointing to the bottom right. And E2 vector will be K times negative 2Q over d squared, and then the unit vector should be negative R1 hat. Why? Because when we need to consider the R2 hat is due to this Q2. So we start from this Q2 and then going to the top left. So in such a way, R2 is pointing to the top left. So in such a way, R2 hat is also pointing to the top left. So R1 hat and R2 hat actually points to the opposite direction. So here, this one is actually R2 hat. But if we define many R1 hat, R2 hat, R3 hat, then we have no way to compute. So we just substitute R2 hat to be negative R1 hat here. Okay, so for the E3 will be K times K times a negative 4Q over d squared, and then in that case, R3 we consider to start from this Q3 and then pointing to here. So the axis R3 is pointing to the bottom left, and so as this R3 hat is also pointing to the bottom left. But okay, so this is actually R3 hat. No, don't need this parenthesis. Okay, so in such a way we can do some simplification. This is actually K times 2Q and then over d square, and then times r1 hat. Okay, so because we have this this minus I and this minus I, okay, combine them to be a positive sign, and then here we have a negative k 4q over d square r3 hat. Okay, so actually the total E field at the original point is actually E1 plus E2 plus E3. Okay, so this will actually be 2 times E3 cosine 30 degree and then I hat. Okay, why is it like that? Okay, so actually E1, E2, okay, we can simply observe that these E1 and E2 are actually the same, pointing to with the same magnitude and also pointing to the same direction, which is here, E1 and E2 pointing to the same direction. So in such a way, we can also draw it as something like this. Okay, so the total magnitude will be k times 4q over d squared, and for the E3. This one and this one should have the same magnitude. Okay, and actually we have a negative R3 hat, so which means R3 hat is pointing to the bottom left. So in such a way, negative R3 hat is pointing to the top right. Okay, and then also this one with the same magnitude, Okay, so as long as like this, okay, we have E1 plus E2 is this one, E3 is this one. So E1 plus E2 plus E3, you can easily think that the y-axis component cancel each other. So the remaining one is actually the x-axis component. Okay, so the x-axis component for this one will be this one multiplied by this is 30 degrees, so it is cosine of 30 degree. Okay, and for both E1 plus E2 and E3, so we have two of them. Okay, and then this is the positive axis direction, so we have an I hat here. Okay, so in this case, we can actually put in the value here. So this is actually 2k and then 4q over d square, and then cosine of 30 degree is square root of 3 over 2, and then I hat. Okay, so we can plug in the numbers. So this is actually, okay, actually in the textbook it doesn't try to plug in all the numbers. Okay, it still remains this k. So finally the answer will be 6.93k. Q we also don't know. Okay, so the question doesn't give you the value of capital Q and also the D. So finally the answer will be something like this. Okay, so this is the answer to question A. So this is the net electric field produced at the origin by these free charge particles. Okay, so far it's still very simple. Okay, so next we try to talk about the electric field due to a dipole. Okay, so a dipole. Okay, so in Chinese this is called 电偶. 电偶写好一点啊，电偶啊，不是这个是偶，OK， 通常的话也会叫 electric dipole 啊 ，electric dipole， 因为也有 magnetic dipole， 所以 那现在的话只叫了这个 electric dipole， 所以它这里就只说 dipole， 但是全写的话应该叫 electric dipole 啊，这里就是这么叫的，就是电偶啊，电偶。电偶的话，你顾名思义的话，就是有两个电子啊，有两个电子。Okay, so the definition of the electric dipole is electric dipole consists of two particles with charges of equal magnitude but opposite sign, separated by a small distance. 所以它有几个条件有几个条件。首先的话，它是有两个电荷然后它的电荷量的大小是相等的，但是符号相反，一个正一个负，然后大小一样。然后 separate by a small distance， 然后隔着一个很短的距离。你说它怎么存在？因为一个正一个负不是应该会吸引吗？它都碰在一起嘛？那其实就不是就不是，因为你高中化学的话应该有学过一个类似的，就比如说水分子，但我不是在教化学那只是大概告诉你说为什么这个世界上有这么奇怪的东西就是说那你高中化学就会学过嘛，它就是类似像一个负电荷一个正电荷这样的，然后它也保持着一个很短的距离，它就是类似像这样一个极性的分子。Okay, so in practical world there should be some dipole in somewhere. Okay, so and here for this dipole we will define a physical variable 会定义一个物理量叫做 electric dipole moment. Although here is just mentioned the dipole moment, but actually it should be electric dipole moment. Of course, as I mentioned, there should also be magnetic dipole moment. Yeah. So electric dipole moment is also a vector. So the definition of the electric dipole moment P is something like this. It is the Q times D vector. Q times D vector. Q is actually this magnitude Q. This magnitude is this one, and then the distance. Okay. We make it a vector. Okay, how to define the direction? The direction of the D is, okay, you can actually check out this figure. Okay, so this one is the dipole. Okay, so this is a negative charge and then the positive charge. And then this one will be positive Q and then this one will be negative Q. Okay, so the distance, so the D vector, the magnitude of D will be the distance between these two charged particles D. Okay, and then the direction is starting from the negative charge to the positive charge. Okay, so from the negative charge to the positive charge will be the direction of the D vector. Okay, so in such a way we have P vector equals QD. Here for the Q we also use the positive sign. So in that way both D and P points to the same direction. Okay, this is also a vector. Something like this. So this is a definition of the electric dipole moment or the dipole moment. Okay, so for the SI unit is coulomb meter. Okay, very straightforward. The SI unit for the Q is coulomb, and then for the SI unit for the distance should be meter. Okay, so this is C times M. Okay, so here it says the magnitude of the electric field set up by an electric dipole at the distance point on the dipole axis, which runs through both particles, can be written as this expression. Okay, looks a little bit horrible, but actually I will derive it in the next page. Okay, so let's slightly take a look at this equation. Okay, so this is the E field generated by a dipole, but this formula can only express the E field along the dipole axis， 就是这个 dipole moment 的那个轴的方向。什么意思？就是说，其实它也会在整个空间会产生电场，但是我们只针对连接它们的这个轴啊，这个轴的表达式才会比较 elegant 啊，才会比较 elegant。在外面的话就会没有办法算出一个很漂亮的公式啊，所以这个公式只代表这个 dipole moment 连接这两个电荷的这个轴的方向啊，当然可以正可以负的，就是我们定义这个 dipole moment 的中间点为0啊。然后往一个方向是正的，往另外一个方向是负的啊。对，就是往正电荷的那个方向是正的，往负电荷的那个方向是负的。Okay, so here we can also see this is the K, 1 over 4 pi epsilon naught, and then here we have a QD. QD is actually this P. Okay, so here we also write it as P. And then here we have a C cube. Oh, you may ask why it is C cube rather than C square. And then you may also ask, why do we put a 2 here? Why don't we cancel this 2 and that 4? Okay, so the simple answer to this one is usually this big constant will appear together. Of course, you can actually write it as a 1 over 2 pi epsilon naught and then times QD over C cube. Of course, it is correct. Of course, this is correct, but yeah, sometimes if you need to use this formula and then you see this constant, maybe you are not careful enough to recognize that, this is a 2 rather than a 4, and then you just substitute this is 8 times 9 times 10 to the 9th power, and then you make mistakes. So if I try to write it as 1 over 4 pi epsilon naught and then times another 2, and then even though you are not that careful, then you will still, this one is 8.99 times 10 to the 9th power. This is another 2. So you don't make that mistake. Okay, so I intentionally make it like this here. Okay, and here for this elegant formula, we have assumption. So the assumption here is that where z is the distance between the point and the center of the dipole, 就是两个电荷的中心点啊。And then assuming z is much larger than d, okay， 就是两个大于符号的话，就是远大于啊，就是高中可能已经会看过嘛。那但是工程的学生的话，其实会蛮常会有这种的，因为其实有这个远大于的符号的话，代表说它可以做一些近似啊，做一些 approximation。那近似的话有什么好处？就是公式就会看起来比较简单啊，但它会有一些误差。但是如果误差不是很大的话，那我们就希望我们的生活简单一些啊，所以就做一些简化。OK， 所以就会有一个z 这个距离，就比如说我们关心这个轴上面某一点z， 在这个图上面是在这个位置啊，这个位置。那 z 的话就是说 z 的话就是说从中心点算到这个点的距离啊，这个就是 z。z 远大于这个 d 啊，虽然这个图看起来没有大很多，可能2-3倍，就数学上不算是远大于啊，可能一般可能会大于5倍啊、10倍以上才称为这个，但是看你的误差能接受的范围。所以这个远大于到底多大算远大于的话，没有一个严格的标准，看你的误差能接受多少。如果越大的话，当然这个误差就会越小。但是这个图我没有办法画得非常的夸张我没有办法画个10倍给你看，因为不然的话这两个电荷就碰在一起。所以的话就是大概示意图是这样然后说假设说这个 z 远大于 d 它就会变成一个比较优雅的形式。Okay, so let's have a 15 minutes break and then we continue.